Hi. You've seen that the job of a programmer is to design processes that accomplish particular goals, such as finding the square roots of numbers or other sorts of things that you might want to do. We haven't introduced anything else yet. Of course, the way in which a programmer does this is by constructing spells, which are constructed out of procedures and expressions, and that these spells are somehow direct a process to accomplish the goal that was intended by the programmer. In order for the programmer to do this effectively, he has to understand the relationship between the particular things that he writes, these particular spells, and the behavior of the process that he's attempting to control. So what we're going to do in this lecture is attempt to establish that connection in as clear a way as possible. What we will particularly do is understand how particular patterns of procedures and expressions cause particular patterns of execution, particular behaviors from the processes. Well, let's get down to that. I'm going to start with a very simple program. This is a program to compute the sum of the squares of two numbers. I will define the sum of the squares of x and y to be the sum of the square of x, I'm going to write it that way, and the square of y, where the square of x is the product of x and x. Now, supposing I were to say something to this, like to the system after having defined these things, of the form the sum of the squares of 3 and 4. I am hoping that I will get out a 25, because the square of 3 is 9, the square of 4 is 16, and 25 is the sum of those. But how does that happen? If we're going to understand processes and how we control them, then we have to have a mapping from the mechanisms of this procedure into the way in which these processes behave. What we're going to have is a formal or semi-formal mechanical model whereby you understand how a machine could, in fact, in principle, do this. Whether or not the actual machine really does what I'm about to tell you is completely irrelevant at this moment. In fact, this is an engineering model. In the same way that an electrical resistor, we write down a model V equals IR, it's approximately true. It's not really true. If I put enough current through the resistor, it goes boom. So the voltage is not always proportional to the current. But for some purposes, the model is appropriate. In particular, the model we're going to describe now, which I call the substitution model, is the simplest model that we have for understanding how procedures work and how processes work, okay? How procedures yield processes. And that substitution model will be accurate for most of the things we'll be dealing with in the next few days. But eventually, it will become impossible to sustain the illusion that that's the way the machine works, and we'll go to other more specific and particular models that will show more detail. Okay, well, the first thing, of course, is we say, what are the things we have here? We have some cryptic symbols. And these cryptic symbols are made out of pieces. They're kinds of expressions. So let's write down here the kinds of expressions there are. And we have, and so far, I see things like numbers. I see things like symbols like that. We have seen things before like lambda expressions, but they're not here. I'm going to leave them out. Lambda expressions. We'll worry about them later. Things like definitions. Things like conditionals. And finally, things like combinations. These kinds of expressions I'll worry about later. These are special forms. There are particular rules for each of these. I'm going to tell you, however, rules for doing the general case. How does one evaluate a combination? Because, in fact, over here, all I really have are combinations and some symbols and numbers. And the simple things like a number, well, it will evaluate to itself. In the model I will have for you, the symbols will disappear. Okay, they won't be there at the time when you need them, when you need to get at them. So the only thing I really have to explain to you is how do we evaluate combinations. Okay, let's see. So first I want to get first slide. Okay, here is the rule for evaluating an application. Okay. What we have is a rule that says to evaluate a combination, there are three parts to the rule. The combination has several parts. It has operators and it has operands. The operator turns into a procedure. If we evaluate the operator, we will get a procedure. And you saw, for example, how type plus at the machine, and out came compound procedure something or other. Okay? And the operands produce arguments. Once we've gotten the operator evaluated to get a procedure and the arguments evaluated to get arguments, the operands evaluated to get arguments, we apply the procedure to the arguments by copying the body of the procedure, which is the expression that the procedure is defined in terms of. What is it supposed to do? Substituting the arguments supplied for the formal parameters of the procedure, okay, the formal parameters being the names defined by the declaration of the procedure. Then we evaluate the resulting new body, the body resulting from copying the old body with these substitutions made. It's a very simple rule. And we're going to do it very formally for a little while. Because for the next few lectures, what I want you to do is you say, if I don't understand something, be very mechanical and do this. So let's see. Let's consider a particular evaluation, the one we were talking about before. The sum of the squares of 3 and 4. Okay? Well, what does that mean? It says, I can find out what sum of squares is. It's some procedure. And I'm not going to worry about the representation of that. I'm not going to write it on the blackboard for you. And the 3 represents some number. But if I have to repeat that number, I can't tell you the number. The number itself is some abstract thing. There's a numeral which represents it, which I'll call 3. And I'll use that in my substitution. And 4, okay, is also a number. I'm going to substitute 3 for x and 4 for y in the body of this procedure that you see over here. Here's the body of the procedure. It corresponds to this combination, which is an addition. So what that reduces to, as a reduction step we call it, it's the sum of the square of 3 and the square of 4. Now, what's the next step I have to do here? I say, well, I have to evaluate this. According to my rule, which you just saw on that overhead or slide, okay, what we had was that we have to evaluate the operands, and here are the operands. Here's one, and here's the next operand. And we have to evaluate the procedure. The order doesn't matter. And then we're going to apply the procedure which is plus, and magically somehow that's going to produce the answer. Because I'm not going to tell you, I'm not going to open up plus and look inside of it. However, in order to evaluate the operands, let's pick some arbitrary order and do them. I'm going to go from right to left. Well, in order to evaluate this operand, I have to evaluate the parts of it by the same rule. And the parts are, I have to find out what square is. It's some procedure, which has a formal parameter x. And also, I have an operand, which is 4, okay, which I have to substitute for x in the body of square. So the next step is basically to say that this is the sum of the square of 3 and the product of 4 and 4. Of course, I could open up asterisk if I liked, well, the multiplication operation, but I'm not going to do that. I'm going to consider that primitive. So, and of course, at any level of detail, if you look inside this machine, you're going to find that there's multiple levels below that you don't know about. Okay? But one of the things we have to learn how to do is ignore details. The key to understanding complicated things is to know what not to look at. and what not to compute, and what not to think. So we're going to stop this one here and say, oh yes, this is the product of two things. Okay, we're going to do it now. So this is nothing more than the sum of square of 3 and 16. And now I have another thing I have to evaluate. But that's square of 3, well, it's the same thing. That's the sum of the product of 3 and 16, which is the sum of 9 and 16, which is 25. So now you see the basic method of doing substitution. And as I warn you that this is not a perfect description of what the computer does. But it's a good enough description for the reasons, for the problems that we're going to have in the next few lectures, that you should think about this religiously. Okay, this is how the machine works for now. Later it will get more detailed. Okay? Now, of course, I made a specific choice of the order of evaluation here. There are other possibilities. If we go back to this, to the telestrator here, and look at the substitution rule, we see that I evaluated the operator to get the procedures, and I evaluate the operands to get the argument first before I do the application. It's entirely possible, and there are alternate rules called normal order evaluation, whereby you could do the substitution of the expressions which are the operands for the formal parameters inside the body first. And you'll get also the same answer. But right now, for concreteness, and because this is the way our machine really does it, I'm going to give you this rule, which has a particular order. But that order is to some extent arbitrary too. In the long run, there are some reasons why you might pick one order or another, and we'll get to that later in this subject. Okay, well now, the only other thing I have to tell you about, just to understand what's going on, is let's look at the rule for conditionals. Conditionals are very simple, and I'd like to examine this. Okay, a conditional is something that has is if, there's also cond, of course, but I'm going to give names to the parts of the expression. It's a predicate, which is a thing that is either true or false, and there's a consequent, which is the thing you do if the predicate is true, and there's an alternative, which is the thing you do if the predicate is false. It's important, by the way, to get names for the parts of things, or the parts of expressions. One of the things that every sorcerer will tell you is if you have the name of a spirit, you have power over it. Okay? So you have to learn these names so that we can discuss these things. Okay? So here we have a predicate, a consequent, and an alternative. And using such words, we see that an if expression, the problem is you evaluate the predicate expression. If that yields true, then you then go on to evaluate the consequent. Otherwise, you evaluate the alternative expression. Okay. So I'd like to illustrate that now in the context of a particular little program. I'm going to write down a program which we're going to see many times. This is the sum of x and y done by what's called piano arithmetic, which is all we're doing is incrementing and decrementing. Okay? And we're going to see this for a little bit. It's a very important program. If x equals 0, then the result is y. Otherwise, this is the sum of the decrement of x and the increment of y. We're going to look at this a lot more in the future. Let's look at the overhead. So here we have this procedure, and we're going to look at how we do the substitutions, the sequence of substitutions. Okay. Well, I'm going to try to add together 3 and 4. Well, using the first rule that I showed you, we substitute 3 for x and 4 for y in the body of this procedure. The body of the procedure is the thing that begins with if and finishes over here. So what we get is, of course, if 3 is 0, then the result is 4. Otherwise, it's the sum of the decrement of 3 and the increment of 4. But I'm not going to worry about these yet, because 3 is not 0. So the answer is not 4. Therefore, this if reduces to an evaluation of the expression, the sum of the decrement of 3 and the increment of 4. Continuing with my evaluation, the increment I presume to be primitive, and so I get a 5 there. Okay, and then the decrement is also primitive, and I get a 2. And so when I change the problem into a simpler problem, instead of adding 3 to 4, okay, then I'm adding 2 to 5. The reason why this is a simpler problem is because I'm counting down on x, and eventually then x will be 0. So much for the substitution rule. In general, I'm not going to write down intermediate steps when using substitutions having to do with ifs, because they just expand things too complicated. What we will be doing is saying, oh yes, the sum of 3 and 4 results in the sum of 2 and 5. It reduces to the sum of 2 and 5, which in fact reduces to the sum of 1 and 6, which reduces to the sum of 0 and 7 over here, which reduces to a 7. Okay? That's what we're going to be seeing. Are there any questions for the first segment yet? Yes?
You're using 1 plus and minus 1 plus. Are those primitive operations?
Yes. One of the things you're going to be seeing in this subject is I'm going to, without thinking about it, introduce more and more primitive operations. There's presumably some large library of primitive operations somewhere, okay, but it doesn't matter that they're primitive. There may be some manual that lists them all. If I tell you what they do, you should say, oh, yes, I know what they do. So one of them is the decrementer, minus 1 plus, and the other operation is increment, which is 1 plus. Thank you. That's the end of the first segment. Now that we have a reasonably mechanical way of understanding how a program made out of procedures and expressions evolves a process, I'd like to develop some intuition about how particular programs evolve particular processes, what the shapes of programs have to be in order to get particular shaped processes. Now, this is a question about really pre-visualizing, as a word from photography. I used to be interested in photography a lot, and one of the things you discover when you start trying to learn about photography is that you say, gee, I'd like to be a creative photographer. Now, I know the rules. I push buttons and I adjust the aperture and things like that. But the key to being a creative person, partly, is to be able to do analysis at some level, to say, how do I know what it is that I'm going to get on the film before I push the button? Can I imagine in my mind the resulting image very precisely and clearly, okay, as a consequence of the particular framing, of the aperture I choose, of the focus, and things like that? That's part of the art of doing this sort of thing. And a lot of that involves, learning a lot of that involves things like test strips. You take very simple images that have varying degrees of density in them, for example, and examine what those look like on a piece of paper when you print them out. You find out what is the range of contrasts that you can actually see, and what in a real scene would correspond to the various levels and zones that you have of density in an image. Well, today I want to look at some very particular test strips, and I suppose one of them I see here is up on the telestrator, so we should switch to that. It's a very important pair of programs for understanding what's going on in the evolution of a process by the execution of a program. What we have here are two procedures that are almost identical. Almost no difference between them at all. It's a few characters that distinguish them. These are two ways of adding numbers together. The first one, which you see here, okay, the first one is the sum of two numbers, just what we did before, is if the first one is 0 and the answer is the second one. Otherwise, it's the sum of the decrement of the first and the increment of the second. And you may think of that as having two piles. And the way I'm adding these numbers together to make a third pile is by moving marbles from one to the other. Nothing more than that. And eventually, when I run out of one, then the other is the sum. However, the second procedure here doesn't do it that way. It says if the first number is 0, then the answer is the second. Otherwise, it's the increment of the sum of the decrement of the first number and the second. So what this says is add together the decrement of the first number and the second, a simpler problem, no doubt, and then change that result to increment it. And so this means that if you think about this in terms of piles, it means that I'm holding in my hand the things to be added later. Okay? And then I'm going to add them in. As I've slowly decreased one pile to 0, I've got what's left here, and then I'm going to add them back. Two different ways of adding. The nice thing about these two programs is that they're almost identical. The only thing is where I put the increment. A couple of characters moved around. Now I want to understand the kind of behavior we're going to get from each of these programs. Just to get them firmly in your mind, I usually don't want to be this careful, but just to get them firmly in your mind, I'm going to write the programs again on the blackboard, and then I'm going to evolve a process. And you're going to see what happens. We're going to look at the shape of the process as a consequence of the program. So the program we started with is this. The sum of x and y says if x is 0, then the result is y. Otherwise, it's the sum of the decrement of x and the increment of y. Now, supposing we wish to do this addition of 3 and 4, the sum of 3 and 4. Well, what is that? It says that I have to substitute the arguments for the formal parameters in the body. I'm doing that in my mind. And I say, oh yes, 3 is substituted for x, but 3 is not 0. So I'm going to go directly to this part and write down the simplified consequent here, because I'm really interested in the behavior of addition. Well, what is that? That therefore turns into the sum of 2 and 5. In other words, I've reduced this problem to this problem. Then I reduce this problem to the sum of 1 and 6. And then going around again once, I get the sum of 0 and 7. And that's one where x equals 0, so the result is y. And so I write down here a 7. So this is the behavior of the process evolved by trying to add together 3 and 4 with this program. For the other program, which is over here, I will define the sum of x and y. And what is it? If x is 0, then the result is y, almost the same. Otherwise, the increment of the sum of the decrement of x and y. No. I don't have my balancer in front of me. OK, well, let's do it now. The sum of 3 and 4. Well, this is actually a little more interesting. Of course, 3 is not 0 as before. So that results in the increment of the sum of the decrement of x, which is 2 and 4, which is the increment of the sum of 1 and, the increment of the increment. What I have to do now is compute what this means. I have to evaluate this. Oh, but that is the result of substituting 2 and 4 for x and y here. Oh, but that is the increment of the sum of 1 and 4, which is, well, now I have to expand this. Okay? But that's the increment of the increment of the increment of the sum of 0 and 4. Okay? But now I'm beginning to find things I can do. the increment of the increment of the increment of, well, the sum of 0 and 4 is 4. The increment of 4 is 5. So this is the increment of the increment of 5, which is the increment of 6, which is 7. Two different ways of computing sums. Now let's see. These processes have very different shapes. I want you to feel these shapes. It's the feeling for these shapes that matters. Okay. What's some things we can see about this? Well, somehow this is sort of straight. It goes this way, straight. This right edge doesn't vary particularly in size. Whereas this one, I see that this thing gets bigger and then it gets smaller. So I don't know what that means yet, but what are we seeing? We're seeing here that somehow these increments are expanding out and then contracting back. I'm building up a bunch of them to do later. I can't do them now. Okay. There's things to be deferred. Well, let's see. I can imagine an abstract machine. There's some physical machine, perhaps, that can be built to do it, which in fact executes these programs exactly as I tell you, substituting character strings in, like this. Such a machine, the number of such steps is an approximation to the amount of time it takes. So this way is time. And the width of the thing is how much I have to remember in order to continue the process. This much is space. And what we see here is a process that takes a time which is proportional to the argument x, okay? Because if I made x larger by 1, then I'd have an extra line. So this is a process which is time. The time of this process is what we say order of x. That means is proportional to x by some constant of proportionality. And I'm not particularly interested in what that constant is. The other thing we see here is that the amount of space this takes up is constant. It's proportional to 1. So the space complexity of this is order of 1. We have a name for such a process. Such a process is called an iteration. And what matters here is not that some particular machine I designed here and talked to you about and called a substitution machine or whatever, substitution model, managed to do this in constant space. What really matters is this tells us a bound. Any machine could do this in constant space. This algorithm, represented by this procedure, is executable in constant space. Now, of course, the model is ignoring some things, standard sorts of things, like numbers that are bigger take up more space, and so on. But that's a level of abstraction at which I'm cutting off. How you represent numbers, I'm considering every number to be the same size. Yeah, and numbers grow slowly with the amount of space they take up and their size. Now, this algorithm is different in its complexity. Okay? As we can see here, this algorithm has a time complexity which is also proportional to the input argument x. That's because if I were to add 1 to 3, if I made a larger problem, which is larger by 1 here, then I'd add a line at the top and I'd add a line at the bottom. And the fact that it's a constant amount, like this is twice as many lines as that, is not interesting at the level of detail I'm talking about right now. So this is a time complexity order of the input argument x. And space complexity, well, this is more interesting. I happen to have some overhead, which you see over here, which is constant, approximately, constant overhead. But then I have something which increases and decreases, and it's proportional to the input argument x. The input argument x is 3. That's why there are 3 deferred increments sitting around here. See? So the space complexity here is also order x. Okay? And this kind of process, name for the kind of process, this is a recursion. A linear recursion, I will call it, because of the fact that it's proportional to the input argument in both time and space. this could have been a linear iteration. We'll say, what's the essence of this matter? Okay, this matter isn't so obvious. Maybe there are other models by which we can describe the differences between iterative and recursive processes, because this is hard now. Remember, those are both recursive definitions. What we're seeing there are both recursive definitions, definitions that refer to the thing being defined in the definition. But they lead to different shaped processes. And there's nothing special about the fact that the definition is recursive that leads to a recursive process. Okay. Well, let's think of another model. I'm going to talk to you about bureaucracy. Bureaucracy is sort of interesting. Here we see on the slide an iteration. An iteration is sort of a fun kind of process. Imagine that there's a fellow called GJS, that stands for me. Okay? And he's got a problem. He wants add together 3 and 4. This fellow here wants add together 3 and 4. Well, the way he's going to do it, he's lazy, is going to find somebody else to help him do it. The way he finds someone else to help him do it and says, well, give me the answer to 3 and 4 and return the result to me. He makes a little piece of paper and says, here's a piece of paper, you'd solve this problem, and give the result back to me. Okay? Now this guy, of course, is lazy too. He doesn't want to see this piece of paper again. Okay? He says, oh yes, produce a new problem, which is the sum of 2 and 5, and return the result back to GJS. I don't want to see it again. This guy does not want to see this piece of paper. Okay? And then this fellow makes a new problem, which is the addition of the sum of 1 and 6, and he says, well, gives it to this fellow, says, produce that answer and return it to GJS. And then that produces a problem which is to add together 0 and 7 and give the result to GJS. This fellow finally just says, oh yeah, the answer is 7, and sends it back to GJS. That's what an iteration is. By contrast, a recursion is a slightly different kind of process. This one involves more bureaucracy. It keeps more people busy. It keeps more people employed. Perhaps it's better for that reason. But here it is, I want the answer to the problem 3 and 4. So I make up a piece of paper, it says, give the result back to me. Give it to this fella. This fella says, oh yes, I will remember that I have to add later, and I want to get the answer to the problem 2 plus 4, give that one to Harry, and have the result sent back to me. I'm Joe. When the answer comes back from Harry, which is a 6, I will then do the increment and give that 7 back to GJS. So there are more pieces of paper outstanding in the recursive process than the iteration. There's another way to think about what an iteration is and the difference between iteration and recursion. You see, the question is, how much stuff is under the table? If I were to stop, supposing I were to kill this computer right now, okay? And at this point I lose the state of affairs, okay? Well, I could continue the computation from this point, because everything I need to continue the computation is in the variables that were defined in the procedure that the programmer wrote for me. An iteration is a system that has all of its state in explicit variables. Whereas the recursion is not quite the same. If I were to lose this pile of junk over here, and all I was left with was a sum of 1 and 4, that's not enough information to continue the process of computing out the 7 from the original problem of adding together 3 and 4. Besides the information that's in the variables of the formal parameters of the program, there's also information under the table belonging to the computer, which is what things have been deferred for later. And of course, there's a physical analogy to this, which is in differential equations, for example, when we talk about something like drawing a circle. Okay? Try to draw a circle. You make that out of a differential equation which says the change in my state as a function of my current state. So if my current state corresponds to particular values of y and x, then I can compute from them a derivative which says how the state must change. And in fact, this, you can see that this draws a circle because if I happen to be, say, at this place over here, at 1, 0, for example, on this graph, then it means that the derivative of y is x, which we see over here. That's 1, so I'm going up. And the derivative of x is minus y, which means I'm going backwards. Okay? I'm actually doing nothing at this point. Then I start going backwards like that as y increases. So that's how you make a circle. And the interesting thing to see is a little program that will draw a circle by this method. Actually, this won't draw a circle because it's a forward Euler integrator and will eventually spiral out and all that. But it'll draw a circle for a while before it starts spiraling. Okay? However, what we see here is two state variables, x and y. And there's an iteration that says, in order to circle, given an x and y, what I want is to circle with the next values of x and y being the old value of x decremented by y times dt, where dt is the time step, and the old value of y being incremented by x times dt, giving me the new values of x and y. Okay. So now you have a feeling for at least two different kinds of processes that can be evolved by almost the same program. And with a little bit of perturbation analysis like this, how you change a program a little bit and see how the process changes, that's how we get some intuition. Pretty soon we're going to use that intuition to build big, hairy, complicated systems. Thank you. Well, you've just seen a simple perturbational analysis of some programs. I took a program that was very similar to another program and looked at them both and saw how they evolved processes. I wanted to give you some variety by showing you some other processes and shapes they may have. Again, we're going to take very simple things, programs that you wouldn't want to ever write. They would be probably the worst way of computing some of the things we're going to compute. But I'm just going to show you these things for the purpose of feeling out how a program represents itself as the rules for the evolution of a process. So let's consider a fun thing, the Fibonacci numbers. You probably know about the Fibonacci numbers. Somebody, I can't remember who, was interested in the growth of piles of rabbits. And for some reason or other, the piles of rabbits tend to grow exponentially, as we know. And we have a nice model for this process is that we start with two numbers, 0 and 1, and then every number after this is the sum of the two previous. So we have here a 1, then the sum of these two is 2, the sum of those two is 3, the sum of those two is 5, the sum of those two is 8, the sum of those two is 13, this is 21, 34, 55, etc. If we start numbering these numbers, say this is the 0th one, and the first one, and the second one, and the third one, and the fourth one, etc., this is the 10th one, 10th Fibonacci number. These numbers grow very fast, just like rabbits. Why rabbits grow this way, I'm not going to hazard a guess. Now, I'm going to try to write for you the very simplest program that computes Fibonacci numbers. It's what I want is a program that, given an n, will produce for me Fibonacci of n. Okay? I'll write it right here. I want the Fibonacci of n, which means this is the n, and this is Fibonacci of n. And here's the story. If n is less than 2, then the result is n, because that's what these are. That's how you start it up. Otherwise, the result is the sum of fib of n minus 1 and the Fibonacci number, the n minus 2. So this is a very simple, direct specification of the description of Fibonacci numbers that I gave you when I introduced those numbers. It represents the recurrence relation in the simplest possible way. Now, how do we use such a thing? Let's draw this process. Let's figure out what this does. Let's consider something very simple, like computing Fibonacci of 4. To compute Fibonacci of 4, what do I do? Well, it says it's not less than 2. Therefore, it's the sum of two things. Well, in order to compute that, I have to compute then Fibonacci of 3 and Fibonacci of 2. In order to compute Fibonacci of 3, I have to compute Fibonacci of 2 and Fibonacci of 1. In order to compute Fibonacci of 2, I have to compute Fibonacci of 1 and Fibonacci of 0. In order to compute Fibonacci of 1, well, the answer is 1. That's from the base case of this recursion. And in order to compute Fibonacci of 0, well, that answer is 0 from the same base case. And here's a 1. And Fibonacci of 2 is really the sum of Fibonacci of 1 and Fib of 0. And in order to compute that, I get a 1. And here I've got a 0. I've built a tree. Now, we can observe some things about this tree. We can see why this is an extremely bad way to compute Fibonacci numbers. Because in order to compute Fibonacci of 4, I have to compute Fibonacci of 2 subtree twice. Okay? In fact, in order to add one more, supposing I want to do Fibonacci of 5, what I really have to do then is compute Fibonacci of 4 plus Fibonacci of 3. But Fibonacci of 3 subtree has already been built. Okay? This is a prescription for a process that's exponential in time. To add 1, I have to multiply by something because I take a proportion of the existing thing and add it to itself to add one more step. So this is a thing whose time complexity is order of, actually it turns out to be Fibonacci of n. This is a thing that grows exactly as Fibonacci numbers. It's a horrible thing. You wouldn't want to do it. The reason why the time has to grow that way is because we're presuming in the model, the substitution model that I gave you, which I'm not doing formally here. I said now spit it out in a simple way, but presuming that everything is done sequentially, that every one of these nodes in this tree has to be examined. And so since the number of nodes in this tree grows exponentially, because I add a proportion of the existing nodes to the nodes I already have to add 1, then I know I've got an exponential explosion here. Now, let's see if we can think of how much space this takes up. Well, it's not so bad. It depends upon how much we have to remember in order to continue this thing running. Well, that's not so hard. It says, gee, in order to know where I am in this tree, I have to have a path back to the root. In other words, let's consider the path I would have to execute this. I say, oh yes, I'm going to go down here. I don't care which direction I go. I have to do this. I have to then do this. I have to traverse this tree in this sort of funny way. Okay. I'm going to walk this nice little path. I come back to here. Well, I got to remember where I'm going to be next. Got to keep that in mind. So I have to know what I've done. I have to know what's left. In order to compute Fibonacci of 4, at some point I'm going to have to be down here. And I have to remember that I have to go back to here, and then go back to here to do an addition, and then go back to here to do an addition of something I haven't touched yet. The amount of space that takes up is the path, the longest path. You know, how long it is. And that grows as n. So the space, because that's the length of the deepest line through the tree, the space is order of n. It's a pretty bad process. Now, one thing I want you to see from this is a feeling of what's going on here. How is this program related to this process? Well, what are we seeing here? There really are only two sorts of things this program does. This program consists of two rules, if you will. One rule that says Fibonacci of n is this sum, which you see over here, which is a node that shapes like this. It says that I break up something into two parts. Under some condition over here, if n is greater than 2, okay, then the node breaks up into two parts. Less than 2. No, it's greater than 2. Yes. The other possibility is I have a reduction that looks like this. Okay? And that's this case. If it's less than 2, the answer is n itself. So what we're seeing here is that the process that got built locally at every place is an instance of this rule. Here's one instance of the rule. Here's another instance of the rule. And the reason why people think of programming as being hard, of course, is because you're writing down a general rule, which is going to be used for lots of instances, that a particular instance is control each particular instance for you. You've got to write down something that's sort of general and in terms of variables, and you have to think of all the things that could possibly fit in those variables, and all of those have to lead to the process you want to work. Locally, you have to break up your process into things that can be represented in terms of these very specific local rules. Well, let's see. Fibonacci's are, of course, not much fun. Yes, they are. You get something called the golden ratio, and we may even see a lot of that sometime. But let's talk about another thing. There's a famous game called the Towers of Hanoi, because I want to teach you how to think about things recursively. The problem is this one. Okay? I have a bunch of disks. I have a bunch of spikes. And it's rumored that somewhere in the Orient there is a 64-high tower, and the job of various monks is to move these spikes in some complicated pattern. So eventually I move all of the disks from one spike to the other. And if it's 64 high, and it's going to take 2 to the 64th moves, then for a long time. The claim is that the universe ends when this is done. Well, let's see. The way in which you would construct a recursive process is by wishful thinking. You have to believe. Okay? So, the idea, supposing I want to move this pile from here to here, from spike 1 to spike 2. Okay? Well, that's not so hard. See, supposing somehow, by some magic, because I've got a simpler problem, I move a 3-high pile to here. I can only move one disk at a time, so I'm not telling you how I did it. But supposing I could do that. Okay? Well, then I could just pick up this disk and move it here. And now I have a simple problem. I have to move a 3-high tower to here, which is no problem. So by 2 moves of a 3-high tower plus 1 move of a single object, I can move the tower from here to here. Now, whether or not it's not obvious in any deep way that this works. And why? Now, why is it the case that I can presume, maybe, that I can move the 3-high tower? Well, the answer is because I'm always counting down. And eventually I get down to a 0-high tower, and a 0-high tower requires no moves. So let's write the algorithm for that. It's very easy. I'm going to label these towers with numbers, but it doesn't matter what they're labeled with. And the problem is to move an n-high tower from a spike called from to a spike called to with a particular spike called spare. That's what we're going to do. Using the algorithm I informally described to you, move of an n-high tower from to with a spare. Well, I've got two cases. And this is a case analysis, just like it is in all the other things we've done. If n is 0, then I'm going to put out some answers. Done, we'll say. I don't know what that means. Okay? Because we'll never use that answer for anything. We're going to do these moves. Else, I'm going to do a move. Move a tower of height less than n, the decrement of n, height. Now, I'm going to move it to the spare tower. The whole idea now is to move this from here to here, to the spare tower. So from to spare, using 2 as the spare tower. Okay? Later, somewhere later, I'm going to move that same n high tower, after I've done this, I'm going to move that same n minus 1 high tower from the spare tower to the 2 tower using the from tower as my spare. So, the spare tower to the 2 tower using the from as the spare. All I have to do now is, when I've gotten it into this condition between these 2 moves of the whole tower, if I've got it into that condition, now I just have to move one disk. Okay? So I'm going to say there's some things for printing a move, and I don't care how it works. From the 2. Now you see, the reason why I'm bringing this up at this moment is this is an almost identical program to this one, in some sense. Okay? It's not computing the same mathematical quantity. It's not exactly the same tree, but it's going to produce a tree. The general way of making these moves is going to lead to an exponential tree. Well, let's do this 4 high. Okay? Now I have my little crib sheet here. Okay, so otherwise I get confused. Well, what I'm going to put in is the question of move a tower of height 4 from 1 to spike 2 using spike 3 as a spare. That's all I'm really going to do. Okay, well, let's just do it. I'm not going to worry about writing out the trace of this. You can do that yourself. Okay? But it's very simple. I'm going to move disk 1 to disk 3. And how did I get to move disk 1 to disk 3? How do I know that? Well, I suppose I have to look at the trace a little bit. Okay? What am I doing here? Well, this is not, n is not 0. So I'm going to look down here. This is going to require doing 2 moves. I'm only going to look at the first one. It's going to require moving. Oh, why do I have move tower? It makes it harder for me. Move. Okay? I'm going to move a 3 high tower from the from place, which is 4, to the spare, which is 2, using 3 as my, no, using from, yes, I'm sorry. Okay, from 1 to 3 using 2 as my spare. That's right. Okay, and then there's another move over here afterwards. Okay, well now I say, oh yes, that requires me moving a 2 high tower from 1 to 2 using 3 as a spare and some other things. And that's going to require me moving a 1 high tower from 1 to 3 using 2 as a spare. Right? Well, and then there's lots of other things to be done. So I move my 1 high tower, okay, from 1 to 3. using 2 as a spare, which I didn't do anything with. Well, this thing just proceeds very simply. I move a disk from 1 to 2, then I move this disk from 3 to 2. Okay? I don't really want to do it. Then I move from 1 to 3. Then I move 2 to 1. Right? Then I move 2 to 3. Then 1 to 3. 1 to 2. Okay? 3 to 2. 3 to 1. It's all got worked out beforehand, of course. 2 to 1. 3 to 2. 1 to 3. Okay? Oh, 1 to 3, excuse me. Thank you. 1 to 2. Okay? And then 3 to 2. Whew. Now, what I'd like you to think about, okay, you just saw a recursive algorithm for doing this, and it takes exponential time, of course. Now, I don't know if there's any algorithm that doesn't take exponential time. It has to. If I'm doing one operation, and I can only do one thing at a time, there's no algorithm that's not going to take exponential time. But, can you write an iterative algorithm rather than a recursive algorithm for doing this? One of the little sort of things I'd like you to think about. Okay. Can you write one that, in fact, doesn't break this problem into 2 subproblems the way I described, but rather proceeds a step at a time using a more local rule? That might be fun. Thank you so much for the third segment. Are there questions?
What's a typical way to reduce the tree recursion problem? How do you save, for instance, the intermediate work you have done in computing the Fibonacci?
Oh, well, that's, in fact, one way. That's one of the ways to do it is what you just said. You said, I save the intermediate work. Okay? Well, let me tell you, this again we'll see later, but suppose it's the case that any time I compute anything, any one of these Fibonacci numbers, I remember it in a table. It takes only linear time to look up the answer. Then if I ever see it again, instead of doing the expansion of the tree, I look it up. I've just transformed my problem into a problem that's much simpler. Now, of course, there are other ways to do this as well. That one's called memoization. You'll see it sometime later in this term. But I suppose there are just very simple linear time and, in fact, iterative models for computing Fibonacci's. And that's another thing you should sit down and work out. And that's important. It's important to see how to do this. I want you to practice.